This is the last video of this series about the thermal reaction norm of sex ratio. The subtitle is All Models Are Wrong. Let's see why I will say this. The conclusion of the first and second parts were that to estimate the population equivalent of the thermal reaction norm for sex ratio, we should use the flexit double star model fitted using Bayesian model. This model must use only data obtained at constant incubation temperatures, and we have seen that the maximum likelihood model was not correct because it shows only one particular solution, not the range of possible solutions. The Bayesian model offers more correct solution. In the third and fourth part, we have seen how to estimate the population equivalent of the thermal reaction norm for sex ratio using a flexit double star model for 3 different RMUs of the same species, and we show that this probability that a single model is sufficient to model these thermal reaction norms was higher than 9.999, both when RMU was included as fixed or random effect. Then, with this data, we concluded that it was improbable that there is an RMU effect. Just take care. We cannot conclude that there is no RMU effect, just that we don't have the data to show this kind of effect. But we have used different models to estimate the pattern of the thermal reaction norm of sex ratio. We have used different models, but we can always imagine other models. And you should always remember, as George Box said in 1978, all models are wrong. Why George Box said this? He said this because a model is just a simplification of the reality. You can have always different models to represent the observation using different hypotheses, and this is not reality. This is a simplification of the reality. Let's see one of the first hypotheses that we did when we modeled the thermal reaction norm of sex ratio. When Claude Piot discovered the temperature-dependent sex determination in turtles in 1971, he wrote, I have translated the original text, as a working hypothesis. It can be considered that in chelonians and perhaps even in all reptiles, optimal temperature conditions are necessary to allow the differentiation of genital glands in accordance with their genetic sex of the embryo. Above this temperature, the genital glands develop into ovaries. Below, they develop into testes. The important point in this sentence is genetic sex. Then, for Claude Piot, the extreme temperatures overpass the action of sex chromosomes and influence the sexual phenotype. In this view, the sex chromosome could influence sexual phenotype only within the transitional range of temperature. This view has been abandoned now, but it has never been invalidated. Let's see what the hypothesis we used when we model our thermal reaction norm of sex ratio. Remember, in the first video of this series, we said if the pattern is represented by a sigmoid equation, the exact value of the TRT depends on asymptotes but never reach 0 or 1, but tends to 0 and 1. Consequently, the TRT defined by the range of temperatures that produce a theoretical sex ratio different from 0 and 1 is infinite. Is it true or not? It's not completely clear. Imagine that we can put 1 million eggs at, for example, in this graph, 26 degrees Celsius. If the TRT is defined as an asymptote, for 1 million eggs, we can suppose to have at least one male in feminizing condition or one female in masculinizing conditions. Honestly, I don't think it can be possible. If TRT is defined as the range of temperature in which sex chromosome can express, this difficulty of TRT definition with sigmoid equation is no more a problem. Let's see how we can do this. We define a new model to describe the thermal reaction norm of sex ratio with two parameters, TRTL and TRTH, being the lower and higher limits of the TRT, and SRTRT being the sex ratio within the TRT. This model is the model that was proposed by Claude Piot in 1971. This is the model in a mathematical point of view, and Claude Piot was more about genetical point of view. If we apply this model to Western Atlantic RMU data of Lepidochelys.olivacea, we obtain these results. I name this model the stairs model because this model is with 3 stairs, all males, intermediate, all females. Let's estimate the TRTL and TRTH and SRTRT values with a Bayesian model. The code is in the description of this video. The Bayesian results are here. Top left, the posterior of the TRTL, at the center, the posterior of the TRTH, and at the right, the posterior of the sex ratio within the TRT. I show here the priors. The priors are all uniform, from 20 to 35 for TRTL and TRTH, and from 0 to 1 for sex ratio within the TRT. The thermal reaction norm. You see here the comparison using WIC and WIC weight, the comparison of the Flexit and stairs model with the West Atlantic data for Lepidochelys.olivacea. We cannot differentiate these two models, but the Flexit model is a little bit favored, but we cannot really exclude the stairs model. What is more interesting is the description of the uncertainty of the TRT for the stairs model. The uncertainty of the stairs model for the lowest part of the TRT is very wide. The limit of the posterior distribution of the TRT is determined by the prior. So even if two temperatures here produce only males, there are so few eggs incubated at this temperature that the model considers that it cannot be used to clearly define the limit of TRT. For the higher limit of the TRT, the model considers that here you have enough 100% female incubation temperature that you can consider that you know the higher limit of the TRT. Now let's try with the 3 RMU that we have for Lepidochelys.olivacea. West Atlantic, we just see these results. East Pacific and Northeast India. Here, and now we compare with WIC and WIC weight if RMU effect can be selected or not. And we show that no, the same as for the Flexit model, we do not detect RMU effect. And when we compare the model, the Flexit model at the bottom and the stairs model at the top with WAC and WAC weight, you see that both models explain similarly the sex ratio, the observed sex ratio. So with this data, we cannot exclude stairs model or Flexit model. So in conclusion, we fit a new model of thermal reaction norm of sex ratio. We named this model the stairs model. In this new model, the TRT is fitted, but the pivotal temperature is not defined. It is not a problem of lack of identification, but pivotal temperature does not exist in the stairs model. At this stage, we don't know if Flexit double star, which is a quantitative genetic model, or the new stairs model, which is a sex chromosome model, explains better the data. Remember, George Box said all models are wrong, but some are useful. And here I think that we are exactly in this situation. We have two models. These two models are wrong because they are not the reality, but they are useful because they permit us to think more about how we can model the thermal reaction norm of sex ratio and how it works deeply for the embryo. And as usual, do not use this kind of model to explain sex ratio from natural condition. This is what we will begin to do in the next video. Thanks.